We have all seen the marketing pitch. Type a prompt, get a flawless 3D model instantly. But when you actually download that file, you don't get a usable asset. You get a broken mess. Raw AI outputs are built on dense, chaotic geometry, known as triangle soup. They frequently pack 1.5 million random polygons and bake the lighting directly into the texture. Standard game engines require about 50,000 clean polygons and neutral textures to actually function. If you drop one of those raw 1.5 million polygon files directly into a game engine or a web viewer, the frame rate will immediately crash. The geometry is simply too heavy for real-time rendering. This creates a trap. If you have to hire a professional 3D artist to manually fix the topology and repaint the textures, you wipe out all the time and money you saved by using AI in the first place. Generating a usable model is not about writing a better text prompt. The actual work happens entirely in the post-generation pipeline, mesh cleanup, and texture baking. Every raw AI mesh requires a specific sequence of operations: cleaning geometry, smoothing normals, and optimizing the final mesh. Since no single software handles this automatically, you must navigate this complex web to pick your specific workflow blueprint. Success in AI 3D generation means looking at your project's final destination, assessing your own technical ability, and choosing the post-processing path that aligns with those constraints. Let's start with the web developer or UI designer building a landing page or prototype. You need visual flair, not a playable video game character. Your pipeline starts by generating a base shape in Formy 3D, and then immediately feeding that geometry straight into Trellis 2. Trellis 2 applies physically based rendering to the model. The materials simulate real-world physics, meaning metal accurately reflects light, and matte fabrics absorb it. The output of this pipeline is a high-quality, photorealistic 2D render. You can quickly generate multiple colorways and material variants to see what fits your design. But you have to accept the trade-off. The output is entirely static. You cannot rig this asset, animate it, or drop it into an interactive game engine. By sacrificing true 3D interactivity, you gain speed. You secure premium, realistic product shots without ever having to learn how 3D modeling or topology actually works. Our second profile is the professional studio or VFX artist. You need characters that can move, be rigged, and scale up for production. This requires a platform like CSM AI, which operates on a premium subscription model running between $20 and $60 a month. The platform integrates Meta's Segment Anything Model 2 to analyze the image and identify individual components. Instead of spitting out a single solid block, it generates distinct part-based meshes. For animation, this structure is mandatory. A single, dense mesh deforms terribly when bent. A part-based topology splits the arms, torso, and head into their own low-poly grids, allowing the character to actually be rigged to a skeleton. To get this automated structure, you are locked into a metered credit system, and you must pay the monthly fee to legally own the commercial rights to your assets. For a well-funded team, trading cash for this automated pipeline makes mathematical sense. It completely removes hours of manual retopology from their schedule. That brings us to the indie game developer. You need lightweight, engine-ready props, but you have zero budget for premium subscriptions. Your pipeline relies on open-source tools. You take a free, high-poly AI-generated mesh and manually process it using a standalone program called Instant Meshes, followed by Blender. First, you run the raw mesh through Instant Meshes to perform quad retopology. This forces chaotic triangles into a clean grid of four-sided polygons. The vertex count drops from 19,000 to 1,200, making it engine-ready. The low-poly model loses its color. In Blender, you bake the texture maps from the high-poly original onto the optimized clone. This route costs nothing, but it demands 10 to 15 minutes of manual labor per asset, alongside a working knowledge of Blender's UV node systems. This is the ultimate sweat equity trade. You convert your human time and technical learning directly into free, highly optimized assets that run smoothly in real time. Before you enter any of these three pipelines, you must decide how you prompt the AI, using a single reference image or using multiple views. A single view prompt preserves incredibly sharp, high-fidelity local details on all front-facing visible regions. But because the AI is blind to the back of the object, it has to guess. This often produces flat, oversimplified, or completely hallucinated rear geometry. Feeding the AI multiple views, front, side, and back, forces cross-view constraints. To solve this, the software uses overlapping data to guarantee global symmetry and structural logic on all sides of the mesh. For a static prop that sits flat against a wall, a single-view input works fine, but if a player needs to walk around or rotate the asset, multi-view inputs are mandatory. Arguing over which AI 3D generator is best misses the reality of the technology. The only thing that matters is matching the tool stack to your specific end goal. To make that decision, use this framework to map your user profile to the ideal tool stack, expected costs, and required skills. If you are a web designer who just needs a product shot, use the Formy and Trellis pipeline to bypass learning 3D topology entirely. If you are an indie developer with no budget, use open-source generators paired with instant meshes and Blender to trade your time for free, engine-ready props. And if you are a pro studio needing riggable characters at scale, invest the monthly premium into CSM AI to buy back your time and keep your focus on game design. Generative AI does not erase the hard work of the 3D pipeline. It simply changes where you choose to spend your resources. Stop searching for a magical one-click button. Identify your specific scenario, pick your toolset, and start executing the optimization blueprint that actually fits your project.